All right, dear students, today we're going to be talking about waves, sound and light. All right, so as you can see here, waves can be divided into categories. They are longitudinal, the ones that can include, for example, sound, and we have also transverse, okay? Transverse waves, and they will be traveling in a transverse, in a perpendicular direction. Okay, so you can see these waves represented this way. Okay, so they will be traveling in a perpendicular direction. While these ones will be represented this way. Okay, so waves carry energy. They never carry mass. They normally carry energy. So it's really important to comprehend this. This means that some waves require a medium to travel, while others do not. Waves that need a medium are called mechanical waves. For example, the longitudinal ones. Okay, but there are other ones that don't require it, and those are called electromagnetic waves. An example of an electromagnetic wave can be light. Okay. Mechanical waves include ocean waves, for example, those ones that you observe when you go to on vacation. So you are like here in obviously we'll have the sea here, the ocean. So if you realize there is going to be a beach ball, right? And the beach ball will be observed as if it was like moving up and down, right? But it will remain the same at the same point. Got it? So these are called mechanical waves. Okay, so electromagnetic waves, they will include something that is really important for human beings, and that's called visible or white light. Also, we have other categories to exemplify this type of waves. We have the X-rays that are used to see throughout our body. We also have radio and television waves. Radio waves are normally used in communication. Okay, so let's go next. Let's go to the next slide. So in this category, which is the visible wavelength category, you can find the electromagnetic spectrum. So you're gonna find that in the Y literal, we're gonna have radio waves that is 10 to the 3. Okay, so with radio waves, for example, we can have a greater wavelength. But what is a wavelength? Wavelength is the distance between crust to crest. Okay, or the distance between trough to trough. Okay, so the horizontal distance between two adjacent crests or troughs is going to be called wavelength. And in physics, we represent the wavelength as lambda. This is wavelength. Okay, so this wavelength will be reduced while we move farther away from the radio waves. So I mean that while we go through this process, reducing the frequency, okay, the wavelength will increase. So frequency is inversely proportional to wavelength. We can say this. I've never seen this expression, but I guess this is a way to express this idea. Okay, so then we have the microwaves. Okay, so before going into the microwaves, let me tell you, the radio waves are normally used to transmit, to broadcast, right, in transmissions, right? For example, you can use these types of waves to broadcast radio and television. Okay, the microwaves, they are used when you cook. So I don't know, but I don't know if you've ever used the microwave. Yeah. And you're going to place here a dish of food. And what the microwaves will be doing will be something like they will make these water molecules vibrate so fast, and the heat energy will increase, right? That's why you can heat your food using this type of waves, right? Also, you can use this in the telephones, right? And its wavelength in meters is 10 to the 2, okay? So we also have the infrared. The infrared goes to 10 to the minus 5. Got it? Okay, we have said that microwaves wavelength is 10 to the minus 2, right? So infrared wavelengths are going to be 10 to the minus 5 meters, okay? Because wavelength can be used in meters, okay? It can be measured in meters. So we have the infrared, and here we don't normally see these types of waves, but we can feel it. We can feel them, right? So they will transmit heat. You can feel heat, for example, from the sun, okay? But also you can find these type of infrared waves in radiators. Okay, so it's normally felt in form of heat, right? Okay, so I'm going to highlight this older type of wave because I consider it's so important. The next one that we're going to be talking about, and this is called the visible wave. So visible wave in the electromagnetic spectrum is going to be basically covering everything that the human eye can observe, right? So we're going to be observing different types of colors. And here is where we have our famous Roy Jeep. Roy Jeep indicates the order of colors that we have when talking about waves. So in science, I normally tell my students, colors don't exist. What exists is waves. Okay, so we have red, okay, we have the orange color, we have yellow, we have blue, green, indigo, and violet. Okay, so in this type of waves, you're going to observe that while, for example, we have some objects with red color, their wavelength will be greater, right? Will be greater. But if you go moving forward, for example, getting close to the violet, the wavelength will decrease, right? So the wavelength is greater when talking about red colors in certain way, is greater than when you talk about of violet colors. So it's really important that with this, for example, you can observe everything that you can see in the case that you're not blinded. No, I blind. Okay. So then we have other types of waves. Okay, so it goes from 5 times 10 to the minus 6, right? That is its frequency, 6 meters. So then we have ultraviolet. So after the violet, that is the last color that we observe in accordance to its wavelength. We're going to talk about ultraviolet. Ultraviolet, that is this one, it's mainly used, for example, or mainly observed when you are like going to the beach, for example, and that this type of wavelength can be absorbed by the skin, used also in fluorescent tubes, right? Okay, so in this case, we can draw something like glasses. Ultraviolet light, for example. Okay, so to protect that can help you protecting your eyes. Okay, so what's next? What we have next can be, all right, so also we can be protected from the ultraviolet rays, right, from the sun. So the sun will be emitting these types of waves. Got it? All right, so next we're gonna talk about the X-rays. So the X-rays, I guess you're so familiar with this concept because normally we use X-rays for many things, right? So X-rays can be found, for example, um, in hospitals, right? In hospitals when you want, for example, when you want to see something related to your body, right? So it's used to view inside of bodies and objects. You can also find this type of waves in the airport, to detect materials that you can take in. Um, Normally, the government will be using this kind of technological gadget to detect these bodies. So then we have the gamma rays, and this can be used in medicine, right? To kill, for example, cancer cells. Okay, so there are therapies that are based on these types of gamma rays, and as you can see, this is the shortest wavelength, right? So I mean that you can observe the atomic nucleus with this. In plural, we say nuclei, right? So with the X-rays, you can observe the atoms. With ultraviolet waves, you can observe molecules. With visible, you can observe protozoans. With an infrared that is of the size of a pinpoint, honeybee, for example, some insects can observe things related to the infrared waves, right? Or microwaves. And humans can be observed, for example, with visible light, right? So if you observe its frequency, the frequency is inversely proportional to the wavelength, right? So the higher frequency in this case, 10 to the 20, right? The lesser wavelength. So the more frequency, the less wavelength, right? It is also related to the temperature. So temperature of bodies emitting a wavelength in Kelvin. So you can observe that 1 Kelvin, 100 Kelvin, our wavelengths will be changing, right? And that is represented by colors here. So we can have, for example, the infrared, or yes, infrared wavelengths, they are closely related to the 1 Kelvin temperature, right? But if you go to the violet, ultraviolet, they will be related to 10 million Kelvin temperature. So now that we have seen this electromagnetic spectrum, I invite you to go to sound. So as we have seen, sound is a type of wave, and this sound carries energy, right? So it's a mechanical wave, and at the same time, it's longitudinal. So its direction is basically is not perpendicular, right? So it goes directly. So this basically is produced by vibrations. So with vibrations, you produce sound. And sound has some properties, right? Characteristics that are intensity, pitch, and it also has timbre. So all of them are going to be related to the wave's properties, right? Okay. As you can see in this image, we humans, like other mammals, are going to have external ear, right? So this creates a perfect structure in an acoustic way to observe the different types of waves. Okay, but in this case, this is a cochlear implant. The cochlear implant that you observe here, uh, it's basically a technological device, right? That contains complex electronic structures that will help us to perceive sound, right? For example, this works perfectly for people who are deaf. Okay, this is for deaf people. And how does it work? It will contain a microphone, which is the one that picks up the sounds, right, from the environment. So basically, the wavelengths will travel in until they crash against this microphone, right, of sound, obviously. So that we have a speech processor that selects and ranges sounds picked up by the microphone, okay? And the transmitter, that is this one, right? Okay, the transmitter, or you can call it a receiver stimulator. And this will receive the signals from speech processor and convert them into electric impulses. So this transmitter, as its name says, will transmit those waves to the middle ear, to the mid ear, right? To the middle ear, right? And an electrode array, which is a group of electrodes that collects the impulses from the simulator and sends them to different regions of the auditory nerve, right? So how does it sound? Obviously, we're going to be using the cochlea, and the cochlea will observe those vibrations, and basically is very different from a hearing aid, because in hearing aids, we amplify sound, right? So they may be detected by damaged ear. By cochlear implants bypass damaged portions of the ear and directly stimulate the auditory nerve, right? So hearing through a cochlear implant, it can be different from normal hearing and takes time to learn and relearn again. Okay, however, it will allow us to recognize warning signals, also to understand different stimuli from the environment and understand speech in person or over the telephone, right? So this is an invention that's being created for people who are deaf. Okay, but going back to the topic, I want to tell you that sound is produced by vibrations. Right, so to have sound, you got to make vibrate the particles that are in the environment. So let's see what's next. So unpleasant sounds, they are called noise, right? So we have some decibels that will measure that. So sound pollution is basically the result of unpleasant sounds that are called noise, right? And they will affect the human health psychologically and physically speaking. All right, so we have sound emission, right? All right, as we have seen, sound is created when an object vibrates. So this causes the surrounding air molecules to also vibrate. Okay, so these vibrations can occur in various ways, such as when a guitar string is plucked, or when, in this case, vocal cords vibrate while speaking, right? So sound waves, for example, the vibrations, in this case of the sound waves, are created due to the pressure that travels through a medium like air, water, or solid materials. These waves are called sound waves and can be classified in longitudinal waves. Okay, but right, so as transverse wave can travel in the air, sound does not fit in this case, right? It doesn't fit because sound needs a medium to travel. So it doesn't travel as in transverse waves in air, right? So the propagation is going to be through a medium that will be used to travel at different speeds depending on factors like temperature, for example, also like density, um, like for example, elasticity, right? How elastic is the body that you're moving. The rubber, for example, is a solid, but if you compare a rubber band um, with the air at 40 Celsius degrees, maybe the sound will travel at a faster speed in the air, right? Okay, so this is basically the explanation for this. All right, so talking on sound reception, um, the outer ear, that is called the pinna or auricle, is gonna be the visible part of our organ, right? So it has like a helix shape, okay? And this visible part will collect sound waves from the environment and will lead them to the ear canal. That is this one, right? This is also known as the auditory canal, right? So in the middle ear, our sound will cause that the tympanic membrane, that is the eardrum, vibrate, okay? So these vibrations are transmitted to three tiny bones that are called ossicles, right? And the ossicles are known as malleus, okay, incus, and stapes. So these ossicles will amplify the sound vibrations and posteriorly will transmit them to the inner ear. So we can observe that in certain way the tympanic membrane is a connection between the middle ear and the inner ear, right? So the stapes in the inner ear will connect to the oval window, right? That is a membrane cover opening the cochlea. That is the spiral shaped structure. Okay, so when stapes vibrates against the oval window, it creates fluid waves in the cochlea. And the cochlea, that is filled with fluid and lined with tiny hair cells, as the fluid moves, it causes these hair cells to bend, right? And different frequencies of sound will stimulate different hair cells that generate electrical signals, and that will be taken by the auditory nerve. So the auditory nerve, let me see, you write it this way, auditory nerve. The auditory nerve will send the electrical signals to the brain, right? So finally the brain will process these signals and interpret them as recognizable sounds. And that is basically the process that we experience in this case. Okay, so many animals, they have external ears, for example, mammals. Okay, so they are basically adapted for locating food or detecting approaching threats. An example can be a rabbit. Okay, so rabbit can detect dangerous situations by pointing their their ears to the potential danger they can be facing. Okay, but there are other animals like dogs, cats, deer, and donkeys that also have large external ears. And also we have animals with small or no external ears. For example, we have snakes, lizards, and birds. Okay. There is other phenomena that is present here. It's called echolocation, right? Animals like bats, for example, they use their ears to echolocate themselves by emitting some sound waves that will bounce off and will be perceived by their ears. So the speed of sound is going to be varying depending the state of matter it is facing to travel. So, for example, sound travels fastest in solids, then liquids, and slowest in gases. But there are other properties as we have said, that will affect sound speed. For example, one of those properties can be temperature. So in this case, for example, we have air, and sound in Earth at 40 Celsius degrees is going to travel at 355 meters per second, right? But at 20 Celsius degrees, we'll travel at 343 meters over second. But also we have other condition that is elasticity. So in rubber, for example, it will travel at 60 meters over second. But in solids, as we have mentioned, it will travel faster, right? Lead, for example, it will travel at 1,210 meters over second, but in gold, it will travel faster, right? So it's really important to recognize these patterns. Let's go to the next subject. Okay, so sound has different physical characteristics such as intensity, that is measured in decibels, right? And we can distinguish the volume between two sounds by its intensity. But more than it, we have the pitch, right? And the timbre. So, for example, a greater amplitude in the sound wave produces higher volume and more energy. For example, in this case, our amplitude will be determining the volume of our sound. And you can observe the differences. For example, a whisper can be 30 decibels, no? So it's 30 decibels. Right? So, but if you compare that with a fireworks rocket launch, is notorious the difference, which is 140 decibels. And that's what we call the volume intensity. Okay, so then we have a pitch, right? And finally, we have timbre. So timbre will allow us to differentiate the body that is emitting sound. So it's not the same, the timbre that is produced by a violin than that one that is produced by your vocal cords. Noise pollution is the excess of disturbing sound that will negatively impact the environment, human health, and well-being. So it is typically caused by activities like traffic, construction, okay, industrial activities, urban activities, household noise, right? And obviously the effects of noise pollution are tremendous. So for example, if you are exposed to high decibels over 85, 80, constantly exposed over 85 decibels, that can damage your hearing, right? Or it also can it also can produce sleep disruption, right? Sleep disruption. So it can produce damage, it can produce sleep disruption, it can produce stress, stress and anxiety, right? It can produce a wildlife impact, right? So this can affect the biodiversity and by altering the food chain and traffic chain, right? So how can we consider that something is noise pollution? Key decibel levels for noise pollution can be, for example, in a quiet environment, you can say that 30 decibels. In a quiet environment, like a library or soft whisper, generally harmless, right? But from 55 to 60 decibels, um, prolonged exposure can cause irritation and stress, such as noise from traffic, vacuum cleaners, or loud conversations. 85 to 100 decibels can also be related to concerts, right? Sirens or airplanes during takeoff fall into this range. So they can cause immediate harm to hearing if the exposure lasts too long. And okay, above 120 decibels in noise at this level, such as explosions, is painful to hear and can cause instant damage to the ears. So we have like thresholds for noise pollution, right? So we have 80, 85 decibels, right? So over 8 hours of being exposed to this, we can experience damage in our hearing. 100 decibels, same, right? To be exposed for more than 15 minutes is so harmful. And 120 decibels, it will produce immediate risk of hearing loss with brief exposure, right? And this is the way that it works. It's quite important to comprehend that it also depends on the context and the environment that we're going through, right? But elephants, for example, they can communicate far away using vibrations. They can produce beating and the terrain. Okay, let's take a short review because we had already seen this. We can say that electromagnetic waves, most of the electromagnetic waves will travel at a velocity of 3 times 10 to the 8 meters of a second, right? That is like speed, okay, or 300,000 kilometers per second, right? And their speed decreases when they travel through gases and liquids. Yeah. Okay, the wavelength and frequency in their cases travel at the same speed in vacuum. They differ in wavelength in frequency, but are gonna be traveling at this speed, right? And the entire range of electromagnetic waves with similar wavelengths and frequency is called the electromagnetic spectrum. That is this one, right? And among these types of subcategories, the visible light is the most important, right? So here there is another representation of electromagnetic waves according to their use. So we have radio signals in these radio waves, the microwaves to heat our food, the infrared when you use a remote control, right? The visible light, that is the light that you can perceive, and those bodies that can be seen by human beings. Ultraviolet, those ones that are related to the sun, right? Ultraviolet rays, we use glasses to protect our eyes and skin from these types of rays. The X-rays are those ones that we use to take radiography, right? With this we can detect strange or foreign objects in our bodies. And gamma rays, these ones that are the last ones, these are the smallest wavelength waves, right? So Gamma rays, with gamma rays, you can observe the atomic nuclei, right? So this is the way that it works. The electromagnetic spectrum in visible light of the entire electromagnetic spectrum, only a small portion can be seen by the human eye. As I explained you, that is the visible light or white light. And that white light will come from the sun. Okay, so visible light consists of the colors we perceive when light reflects off the surface, right? And this is the way that the rainbow can be produced. Right, the eye organ. So the eye is a complex organ that allows us to perceive light and interpret it as visual information. So here we have the structures that will allow us to help you understand. Okay, so first we have the cornea, right? So the cornea, when light enters the eye, it first passes through the cornea. So cornea will help you to focus light by bending it. And this process is known as refraction, right? Then we have the pupil, and that goes after the cornea, and the light moves through the pupil, the dark circular opening in the center of the iris, right? This one, okay, which is the color part of the eye. So the size of the pupil that you observe here adjusts depending on the amount of light constricting it, right? So this is a constricting in bright light and dilating in low light to control how much light enters the eye. So it adjusts depending the amount of light. Okay, then we have the lens. There is this part that you can observe in the interior side. So then the light passes through the lens, right? So the lens will help us to direct the light onto the back of the eye, and it will shape the shape by using the accommodation strategy, right? All right, so then as you can observe in the structure, we're gonna have the retina. So the light will finally reach the retina, that is a layer that consists of specialized cells. Specialized cells here are called rods and cones, right? And they are responsible of detecting light and dark. Okay, light and dark. And cones are responsible to detect color and provide sharp, detailed vision in bright light. Okay. All right. So after this, these signals will be sent to the brain by using the optic nerve. So the optic nerve will be sending these signals, and finally the brain will process these waves and will create the images we see, right? So in summation, the eye captures the eyes and focuses light rays, converting them into signals that the brain can interpret. Okay, so this is the way that we use the eye. The composition of light. So this refers to the process by which white light, as its name says, is decomposed, right? Is separated into its constituent colors, right? There are the famous red, orange, green, blue, indigo, and violet, right? And how does it happen? So when white light passes through a prism, like this one, this is an experiment that was performed and contributed by Newton. Sir Isaac Newton started representing this this experiment, right? So, okay, so when white light passes through a prism, it bends, as you can observe here, right? It bends and it refracts. So it has a refraction process, okay? And this refraction will change the angles depending on the wavelength of each color. This separation creates what we call the spectrum of colors. This is the color spectrum, okay? All right, so this separation will be typically represented by red, orange, yellow, green, blue, indigo, and violet. That are the colors that are shown after the decomposition, right? So the functioning can be basically attributed to the refraction, okay, because light travels at different speeds, sorry. Refraction, because light travels at different speeds in different media. So when light enters a denser medium, like glass in this case, like this prism, it slows down and bends. Also, you can observe that there is a dispersion of colors, okay, because each color has a different wavelength. And because of this, we can observe that red light bends the least, while violet light bends the most. And finally, we have the formation of the spectrum. So the formation of spectrum. So as light continues through the prism, it spreads out to form spectrum. And this is what we call the composition of light. Okay. All right, so let's see what's next. So basically this is the same way how we can form rainbows now. So if you replace the prism by these droplets of water, and you replace the white light by the sun, that gives off white light, you will observe something similar. Okay. Got it? And light will be bent. Okay. Okay. All right, so this is everything for today. I hope you have enjoyed this video. This is Mishael Wright, and see you in the next class.